So, just a reminder, I'm gone Monday, Tuesday. Juniors, Tuesday, Wednesday is when you're getting pulled from my class. So I'm going to try to give you as many details tomorrow as I can, and then the sub will just have to remind you on Monday where to go for Tuesday and Wednesday. Yes?
What are we getting pulled for?
The ACT practice test. You're getting pulled from each of your core classes.
Wait, but I did that last year, or no, like last Saturday. I took the real one. You selected.
So you're taking the ACT practice test through Naviance, which is that online program that you all have, and it'll give you an individualized study plan so that you can use in preparation for April's ACT.
Okay.
Okay?
All right.
All right, this is what I want you to do. As a pod, come up with 3 graphs. Draw 3 graphs in ways that f of x appears differently. And I want you to talk about the slopes and how the slopes are changing. So draw 3 graphs and talk with your pod about how the slopes are changing. Not what the slopes are, but how they're changing. Go. Stronger. And then talk about oh yes, the derivative I want to be positive. So I want all of these to be increasing functions. Thank you for pointing that out. I'm trying to get you going after that fire drill.
Okay, so I drew 2 right off the bat. For this one, we got the slope is increasing. And for the second one, we got the slope is decreasing. You can't accept the decrease.
Yes.
You know, this slope is still positive. It's still positive. But you see, it decreases slightly, so slightly toward the axle. It's great to parabola. Oh, what if we do a cubic function then? We can do. You're telling me.
Here are 2 graphs that I've seen pretty commonly amongst the pods. How are the slopes changing here?
Decreasing.
Our slopes are decreasing because they're getting less steep. How are the slopes changing here?
Increasing.
Increasing because they're getting more steep as we go towards infinity. Okay? Do you see the difference between these 2 graphs? One is like curved down and one is curved up. This, ladies and gentlemen, is concavity right here. Okay, this graph, anyone draw this graph?
Yes, I drew all 3.
It's like we were on the same wavelength.
Yes.
Okay, here our slopes are increasing and then our slopes are decreasing. You see that change? Okay, concave up and concave down. Concave up looks like it would hold water. Concave down looks like it would spill it out. That's what you need to know. Okay? Now, we will talk about how the second derivative is related to concavity, but we first need to get a picture in our head about what is concave up and what is concave down. Okay? Based on what you know from geometry and through your science classes, I think this makes sense, right? This doesn't feel like a totally new concept, concavity. okay? It's actually going to give us a way to better describe curves, which I'm excited about, because I've been avoiding having to use the word concavity because you haven't known really what it was, but now we can use it and describe things better, okay? So let's talk about the two different concavities here. If the derivative is telling us what our slopes are, right? Then our second derivative can tell us how our slopes are changing, okay? So when we talk about the first derivative, it's talking about how the y's are changing over x, right? Slope, change in y over change in x. When we talk about the second derivative, we're talking about the change in the derivative over change in x. So we're talking about how the slopes change. If the first derivative tells us how y is changing over x, tells us about slope, then the second derivative is telling us how the first derivative changes, which is really how the slope is changing. Okay? So I want you to look at these pictures. Concave up. You already described this to me before you knew what concavity was. But as we look at all of these tangent lines, what is happening to our slope? As we go from left to right with concave up, our slopes are getting bigger or smaller? Okay, well, we start negative, right? But as we get less steep in the negative direction, wouldn't those numbers be bigger? Right? And then as we curve around, these slopes get steeper in the positive direction, therefore they get bigger, right? So concave up, our slopes are getting bigger, or our slopes are increasing. Okay. Here with concave down, if we go from left to right, our slopes get less steep in the positive direction. Do you agree? Well, then if we turn to negative slopes, they get more steep. Well, if we have negative steep numbers, they're getting more and more negative, correct? Which means what is happening to all of these slopes? Okay, here our slopes decrease. Okay, well, if our slopes are decreasing or slopes increasing, okay, we can look at the second derivative to figure out what is happening, okay? So if concave up means these slopes are increasing, what kind of second derivative value would you expect to see? Positive. If our slopes are decreasing, what kind of second derivative value would you expect to see? Okay, you're exactly right. Here we go. Second derivative. If the second derivative is positive, we are concave up. It means our slopes are increasing. If our second derivative is negative, that means we are concave down for our function. Our slopes are decreasing. If our second derivative is 0, that means we don't have concavity. So we're going to do something similar to what we did with the first derivative, but we are going to look at the second derivative and see where the second derivative is positive versus negative, and that will tell us about the concavity of our function. Okay? Now, is it possible that our function changes concavity? Right? It can be all sorts of crazy. Okay? An inflection point is what we call a coordinate where our concavity changes. So when we have that change in concavity, we call it an inflection point. What do you think is going to be true about the second derivative at an inflection point? It could equal 0 or undefined. So inflection points occur when the second derivative is 0 or undefined. Okay? We're not going to call these critical numbers because critical numbers are where the first derivative is is 0 or undefined. But where the second derivative is 0 or undefined, those are going to be our possible inflection points. Okay? Now, we talked about yesterday, just because we have a critical number doesn't mean we're going to have a minimum or maximum there, right? We saw that yesterday with that last example. Same thing here. Just because we have a second derivative that is undefined or 0 doesn't mean we will have an inflection point. So here are some examples. Here we have a change in concavity. There's our inflection point. Okay. Here we have a change in concavity. Concave up, concave down. That would be an inflection point. What would be true about the second derivative there? It'd be undefined. The first derivative would be undefined because it's a corner, which means then any derivative after that would also be undefined. Okay. Now, look at this right here. Do we change concavity right here? We don't. But since it's a corner, the first derivative is undefined, which means also the second derivative is undefined, but it's not an inflection point. So just because we find where the second derivative is 0 or undefined doesn't mean it will be an inflection point. We still will have to test. Okay, and then same thing here. An asymptote could cause a change in concavity, but that's obviously not going to be an inflection point. Okay, so basically what we did with our first derivative yesterday and the day before, we are going to do with our second derivative today to look at concavity and inflection points. All right, write this one down. We'll start out nice. Okay, so if I want to look at concavity, we need the second derivative. Well, before we can find this second derivative, we need the first derivative. Okay, everybody together, what is our derivative? Excellent. Our second derivative would be what? 6x. Beautiful. Okay. When we have our second derivative, we need to determine where it is 0 or undefined. Okay. That one's nice, right? I really don't have to do any work, but I'm going to anyway. Okay? 0 would be our possible point of inflection. I am going to do some abbreviations just to save some room up on the screen and on your paper if you so choose. Okay? So like I said, You want to label your number line, because pretty soon we're going to be looking at both. Okay, so I'm going to label my number line to be f double prime because it's the second derivative, and I'm going to put my possible point of inflection on that number line. Okay. Test intervals in the second derivative because that's what we're labeled. So negative numbers will make our second derivative. Positive numbers will make our second derivative. Okay, so this is what we know. We know that we are concave up on the interval 0 to infinity. We know that we are concave down on the interval negative infinity to 0. And since we have a change in concavity, what's happening at 0? We have an inflection point. So we have an inflection point. Point of inflection, inflection point. I do not care how you say it. I don't care what order. Okay, you'll see it both ways. At the coordinate 0 something, where do we go to get that y value?
The original function.
The original function. If we plug in 0, negative 4 is our point of inflection. If I ask you to justify a point of inflection, you would tell me what? There's a change in what? In the second derivative. Make sure you say second derivative, okay? So you need to tell me that the second derivative changes signs, or changes from negative to positive, or positive to negative, whatever it may be. Okay, if I ask you to justify, you need to explain what is happening to your second derivative. Okay, on your quiz Wednesday, I'm going to ask you to do some justification. If you say it changes, you are not going to get full credit. I don't know what it is unless you tell me. Second derivative, or f double prime of x, however you want to say it. But the second derivative is changing, in this case, from negative to positive. Okay? All right. Go ahead and write this one down. Okay. My example says, where is it concave up? But we're going to find all of it anyway, so just write the equation down. Okay? And once you get the equation down, I would like you to find the first and second derivatives, please. Catherine, what do you have for your second derivative?
12x squared minus 12x.
Do you agree with Catherine? Okay. So to determine our possible inflection points, we need to know where our second derivative is 0. In order to do that, what should we do? Factor out of 12x. Left over is x minus 1. So on our second derivative number line, we're going to put 0 and 1. Okay. All right, let's start with easy numbers first. If we plug in 2, 12 times 2 times 2 minus 1 would be positive. To the left of 0, we plug in negative 1. 12 times negative 1 times negative 2 Okay, now you have a suspicion, right?
It's gonna be.
Okay, we plug in 1/2. 12 times 1/2 would be a positive 6. 1/2 minus 1 would be a negative 1/2. You multiply those together for negative. Okay. Okay, so if I wanted concavity, you would tell me that we are concave up from negative infinity to 0 and 1 to infinity. And that we are concave down from 0 to 1. Isn't it amazing what we can figure out about our graph without actually graphing it? Next week we'll is it next week? It might be next week or the week after. One of these weeks coming up, we'll actually get to do all this to figure out what the graph looks like without our calculator. Okay, that's where this is heading. Okay, so let's talk about what is happening at 0 and 1. We have inflection points. So since our second derivative is changing from either positive to negative or negative to positive, we have points of inflection. All right? They are occurring at 0 something and 1 something. Okay? Since we have the original function, we can find them. If we plug in 0, what do we get? 5. And if we plug in 1, so the coordinates 0, 5, and 112 would be our points of inflection. Okay. This fire drill is really... hold on, don't write that down. I'm not sure. We're not going to do this one. We need to get to our graphs. Okay, we're going to look at 2 graphs. So I'm going to give you 30 seconds to draw this graph. Maybe a minute. I'll give you a minute. Make sure you do have it labeled that it is a function graph, because next we're going to look at a graph that is a derivative. Okay, so we're going to look at everything all together. Okay. Increasing. This function is increasing on only one interval. -2 to 1. From here to here. This function is decreasing.
Negative.
Here. -5 to -2. Where else, Trevor? Okay. 1 to 3. since that is the case, Caroline, where do we have a maximum?
1.5.
Okay, here we have a maximum because we're changing from increasing to decreasing, and we have a minimum, Will.
-2,
Okay, great. Now let's look at concavity. We haven't done this before. April, where are we concave down?
1 part.
Okay, 1 to 5. Anywhere else? Mm-hmm. Okay, -3 to -2 is also where we are concave down.
Yeah, those run backwards.
What? Oh. What was it that? Did I ask you down? Okay. Okay, concave up. Ashley, where does it look like we're concave up?
5 to -3. -1 to 1.
Okay, so this is kind of funky, right? So we're concave down here, right? But then it kind of like cups up right here.
So -2.
I would say -2 to -1, because then here at -1 we switch there. All right. So our points of inflection, we have how many of them? 3? 2. We have 3. We have points of inflection at -3, 1, -2, -1, and -1, 1. Okay? Right here, I'll highlight them in blue. We have inflection points. Okay? Now, what I'm going to do is I'm going to go through a derivative graph, and I don't want you to write anything down because I want you to watch and I want you to listen. Okay? If you would like to put this in your notes, then I'll just tell you to go to the video and watch the last couple minutes. Okay? But here we have a derivative graph. If we have a derivative graph, then we look at increasing intervals based on where our derivative is positive. So we would say from 1 to 6 and from, what, 8 to 9?
Yep.
We look at decreasing where our derivative is negative. So 0 to 1 and 6 to 8. Which means we would have a maximum at x equals 6 and a minimum at x equals 1 and 8. Derivatives changing from positive to negative, derivatives changing from negative to positive. Now, if we want to look at concave up, we need to look at where our derivative is doing what? Increasing. If we want where our slope is increasing, well, derivative means slope, right? So our slopes are increasing from 0 to 2, 3 to 5, and 7 to 9, 8, 9, okay, 9. All right, and if I want concave down, we look at where our slopes or our derivative decreases. So concave down from 2 to 3, from 5 to 7. Okay, inflection points, what do they look like on the derivative graph? Where we change directions, inflection point, inflection point, inflection point, inflection point. Okay, so inflection points are your relative minimums and maximums if we're looking at the derivative graph. Okay, we are going to practice this tomorrow as soon as we come in the room. Okay? Hopefully no more fire drills.